In today's lecture for computational aerodynamics and turbulence modeling, we are going to discuss about general behavior of hyperbolic partial differential equation. I myself, Dr. Juluru Sandeep, Assistant Professor, Department of Aeronautical Engineering, IARE. So in the previous modules, we have covered the course outcome 1, 2, and in the present module, we are going to discuss about the course outcome 3, which selects the Cauchy linear partial differential equation for estimating the behavior in the computational fluid dynamics. So in the previous lectures, we have discussed about the methods which are used to classify these partial differential equations, like Cramer's rule method and eigenvalue method, and for the first order differential equations and for the second order differential equations also. So based upon that method, we are going to differentiate the partial differential equations into elliptic, parabolic, and hyperbolic. So now we are going to understand how this behavior is going to affect the CFD solution, or how this behavior is going to help us to define the problem in CFD, or how the CFD approach can be defined to solve these fluid flow problems. So each type of equation has a different mathematical behavior, and this reflects the different physical behavior of the flow fields as well. So, for example, we have the elliptic behavior. So, the elliptic behavior, we have seen some of the examples like incompressible subsonic flows. So, if we consider the hyperbolic form, they are considered as a supersonic flows. So, based upon the behavior, we can understand the physical behavior also. So, based upon the mathematical behavior, whether it comes into elliptic, parabolic, or hyperbolic, so their physical behavior of the flow fields can also be understood. So this implies that different computational methods should be used for solving the equations associated with different classifications or the different fluid flow problems. So once we can identify the behavior of that particular governing equation, we can define the suitable method which can solve those equations and which can give us convergent solutions. So if you are going to define the irrelevant method to the governing equations, then it may lead to a divergent solutions. So first we'll consider the hyperbolic form of equations, how the mathematical behavior is going to be used to develop the CFD approach. So generally the hyperbolic form of equations has the two real roots. Okay, so for any solution point in the domain, it will be having the two real roots. One is in this given problem, we are taking the XY plane two-dimensional domain. So in the two-dimensional domain, we are considering the point P as a solution point. And at this given point, solving the hyperbolic form of equation, it gives the two real characteristic curves. So they are named as the left characteristic curve and the right characteristics curve. And these curves will define the domain of influence or the region of influence or domain of dependence or region of dependence on which the solutions are going to be dependent. So in this figure 1, we are considering the point P, and it is showing us 3 regions. So 3 regions are region 1, region 2, and region 3, and it has a initial data along the y-axis upon which P is going to depend. So we can consider this initial data as boundary condition, or we can consider it as the initial conditions for the domain to be solved. And based upon these, if you extend these right running and left running characteristics before the point P and after the point P, so we will be having certain regions which are going to show the importance of these characteristic lines. So if you see the region 1, the region 1 is influenced by point P, or we call it as region of influence. So that means the solution of the point P is influenced by the region 1. So whatever the solution we are going to obtain, or if you are going to give some disturbance at point P, so it is going to have that region of influence is defined ahead of the point P, and if we extend that particular lines towards the y-axis, so we will be having the region 3. So, and region 3 is going to be considered as domain of dependence. So, that means here you have to understand we have defined that hyperbolic form of equations are solved by marching solutions. So, marching solutions are nothing but they are going to be driven in one particular direction. So, in this case, we are considering the x direction based upon the differential terms in the equation. We are going to have some boundary conditions like A, B, the initial data line. So they are going to be used to solve at point P, or the region 3 is considered as domain of dependence for the solution of point P, and the region 1 is going to consider as domain of influence or region of influence we can consider. So, in that way, the solutions are going to obtained in a forward direction for the given initial conditions. So, we are going to obtain the solution step by step in the given domain. So, for example, when you are going to consider some fluid domain which has been divided into small volumes, okay, so we are defining here boundary conditions, okay, so that the first set of solution will be the inputs to the next set of solution, so the second set of solution will be the input to the third set of solution, so such that it is going in a marching direction in x direction, and we are going to obtain the solution one set of volumes to the other set of volumes, so that we get the throughout the domain. So that is the way how the hyperbolic form of equations are being solved. So without having the two characteristic lines, it is difficult to solve the solution in the marching method. It needs some extra requirements to get the solution easily. So, as said, if you are going to extend the two characteristic lines backward, which they are intersecting with the y-axis, so it is defining the boundary condition for the hyperbolic form of equations, and the dependent variables u and v, the unknowns in the solution in the equations are defined at the y-axis, then the solution can be obtained by marching forward in the distance x, starting from the given boundary conditions. So, in that way, the hyperbolic form of equations are solved by the marching forward, or we call it as marching solutions for the given single boundary condition is enough to obtain. If we are going to consider the hyperbolic form of equations in region 3. So the region 3 is out of the, region 2 is out of the domain with respect to point C, or we can consider it is not similar to the point P. The point C is on the boundary line, or we can consider, so along which we are going to have some particular region. But the solution of point P is not influenced or dependent by this region. So it is not related to this particular region. So it is out of its domain, or we can consider the region 2 is influenced by the solution of point P. In that way, we can differentiate the points, and their approach is going to be defined with respect to the characteristic lines and domain of dependence and the region of influence. So we will can have some particular problems which are in the hyperbolic form of equations, which are solved by the marching solutions. With respect to that approach, the algorithm is designed to start with the given initial conditions about the y-axis as shown in figure 1, and sequentially calculating the flow field step by step marching in the x direction. So in fluid dynamics, we have many problems which comes under this hyperbolic form of equations, and we can see them. Some examples like study inviscid supersonic flow. So in the previous modules, we have discussed some of the examples to understand the Cramer's rule method or the eigenvalue method. So where we have considered two-dimensionally rotational compressible gas over an aerofoil at small angles of attack of thin aerofoil. Uh, Based upon that problem, we could be able to understand that supersonic flows are coming under the hyperbolic form of equations. So let us imagine a supersonic flow over a two-dimensional circular arc aerofoil as sketched in the figure. So the aerofoil can be at an angle of attack, causing the bow shock and the local subsonic flow. So this is one of the interesting problem where the supersonic flow is creating a bow shock, and at the same time that bow shock is generating some local subsonic flows. So we have to define the computational method to solve these two types of flow behaviors. So just defining the method which is related to the hyperbolic behavior will not solve the total problem. So even though when you are solving the hyperbolic form of equation, the marching solution is applied. As it is a supersonic flow, we have the two methods to solve these shock problems. One is shock capturing and the shock fitting. So the shock capturing is a generalized method where for the given boundary conditions or the initial conditions, the total domain is going to be solved and such that the solution is going to be defined with the shock waves, and the generalized method is going to be considered. So if at all you have the shock fitting method, so in the shock fitting method, we are going to define some of the uh, Hugonoid relations to define the shock and to define the area between the shock and the surface. And here these lines, we call it as CD or EF lines, are going to be used to define the initial data for this particular domain. So that is the methods we have to solve the supersonic flow problems. But as said, there are some regions where the flow is going to be subsonic. So solving that particular region by using the hyperbolic form of method will leads to some divergence or the blow up of the conditions, and the solution will not be accurate. So we have to give some special treatment to solve such type of flow problems in the solver or in the algorithm, so that this type of mixed behavior of equations can be solved easily uh, and according to the mathematical behavior. So similarly, if you are going to consider a three-dimensional steady supersonic inviscid flows, uh, just only the one dimension has been increased, but the methodology is going to be same. So here we are also following the marching solution in the x direction, and here the volume of influenced by point P and the domain of dependence for the point P is being shown similar to the previous two-dimensional case, and here the initial data is defined on the YZ plane upon which the P is going to be calculated, and the P solution is influenced in the volume of shaded region in the figure shown. So said that it is following the same uh, methodology to solve either two-dimensional or three-dimensional hyperbolic. So next, coming to the unsteady inviscid flow. So considering the inviscid characteristics, it comes under the Euler's equation, and if the time derivatives of the equations are finite, then the case considered as unsteady flow, and the governing equations comes under the hyperbolic form of equations, no matter whether the flow is subsonic or supersonic. So in the previous case, we have considered the steady flow equations where only supersonic flows comes under the hyperbolic form of equations. But here, irrespective of the subsonic or supersonic, the unsteady inviscid flow comes under the hyperbolic form equations, and in the previous problem, we have considered x, y, or z as a marching direction. But here we are going to consider the time as a marching direction, and the solution is obtained in the fourth dimension, that is time, for the given boundary conditions A and B. It is forwarded in time t. Okay, so and the remaining parts of domain of dependence, region of influence, right running characteristic, left running characteristics, all are going to be considered as same. So this is the one where we can consider the unsteady inviscid flow problems come across us for one-dimensional wave motion in a duct, or two-dimensional unsteady flow over a flapping or plunging aerofoil is the some of the examples where the unsteady inviscid flow is coming across. The most common use of unsteady time marching solution in CFD is to ultimately obtain a steady flow result in the limit of large times, as long as the boundary conditions are constant, or we can consider them as time invariant. So if the boundary conditions are changing with respect to time, then we cannot consider them as a steady flow field, and we have to go for the unsteady solutions only. But if they are in the time invariant, then the steady flow problem that can be solved for the unsteady case in the large times is the one of the probable solution that can be obtained. So these are the major impact of the hyperbolic form of equations and their mathematical behavior and their CFD approach that can be solved. And the content is taken from the computational fluid dynamics, the basics with applications by the J.D. Anderson. So you can refer the other books also to get the more input about these particular topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.